Hermes Agent functions as a multi-agent AI framework designed for autonomous, self-improving memory loops and multi-platform gateway messaging. It represents an engineering effort focused on establishing persistent memory and sandboxing through Daytona and Modal. When integrating a new dependency into an internal automation substrate, organizations expect a standard operational baseline. Software appliances rely on semantic versioning, predictable API schemas, and long-term stability that allows them to be deployed and maintained with minimal intervention. Hermes Agent does not follow this model. The repository is a fast-moving research project where maintainers prioritize the rapid integration of new AI capabilities over backward compatibility and deployment predictability. Attempting to drop a hyper-iterative experimental framework into a production environment as if it were a stable enterprise appliance invites severe architectural vulnerabilities. The resulting infrastructure risk is immense. The sheer momentum of the project reveals its true nature. The repository operates in a hypergrowth phase, routinely absorbing hundreds of pull requests and commits on a weekly basis, bypassing designated stabilization periods. This chart tracks code integration. In exactly 7 days, from version 0.10.0 to 0.11.0, the repository absorbed 1,556 commits and 761 merged pull requests. That release was driven by 290 developers, demonstrating a decentralized approach to code generation. Community requests to implement a predictable monthly long-term support release cadence were actively intercepted and diverted by the core maintainers. Their stated objective is capability expansion, ensuring the software will not conform to standard enterprise stabilization models. Downstream operators cannot rely on upstream governance for operational safety. Organizations capturing the value of this framework must construct deeply fortified, localized perimeters to insulate their internal pipelines from the repository's relentless churn. The immediate consequence of this rapid feature expansion appears in automated continuous integration and delivery pipelines. The repository relies on extensive optional packaging extras. The All installation extra is designed to bundle massive arrays of third-party capabilities directly into the core agent's runtime. This default installation path pulls in heavyweight multimedia integrations, migrating specialized tools like Comfy UI and complex libraries like CTranslate 2 into strict built-in requirements. Invoking this meta package generates an immense interwoven transitive dependency graph. On constrained hardware architectures, attempting to install these fast C++ libraries from source saturates the memory limitations, resulting in complete file system exhaustion and permanent gateway deadlocks. Even in standard environments, the sheer density of this package tree frequently triggers resolution too deep errors, completely paralyzing automated Python build systems. Modern build systems utilize strict lock files, specifically Astral's UV lock, to guarantee that the exact same dependencies are installed across every deployment, ensuring reproducible builds. The maintenance of this lock file within the Hermes repository is chronically inconsistent. New upstream features are added to the project manifest, but the lock file is repeatedly left unregenerated, leaving the explicit package definitions out of sync. When an automated pipeline attempts to synchronize against a stale lock file, the package manager is forced to dynamically re-resolve the entire dependency tree. This blindly introduces transit libraries containing high-severity common vulnerabilities and exposures directly into the core agent's environment. The software's volatile packaging architecture breaks deterministic deployments. Standard continuous integration workflows turn into fragile bottlenecks that break without warning. The operational risk extends past the installation phase and directly compromises configuration state management. Secure enterprise infrastructure relies on declarative deployments. Sensitive credentials, like API keys and database URLs, are kept off the disk and injected exclusively through isolated environment variables. Operators map these environment variables directly into the Hermes config.yaml file using standard template strings. A critical logic flaw exists in the agent's internal load config utility. During initialization, the system proactively evaluates those template strings, resolving the values and holding the plain text secrets in active memory. The safe, abstracted reference remains on disk, while the raw token sits active within the runtime. If an operator triggers a global UI command, the system updates its state. The save config function takes that active memory and immediately serializes it directly back to the disk. The environment variable abstraction is permanently destroyed. Raw authentication tokens are overwritten into the YAML file as unencrypted plaintext. Without rigidly enforced read-only file system permissions, standard operational commands actively sabotage the deployment's security posture. Securing the agent's autonomous execution presents a deeper architectural vulnerability, specifically regarding network authorizations. Hermes maintains a native security perimeter known as the terminal approval gate, designed to block potentially destructive LLM actions against the host operating system. A system command initiated by the model is held pending a strict human confirmation prompt. However, administrators can attach external MCP server nodes. The agent routes execution entirely around the approval gate, allowing the LLM to execute external tools while entirely bypassing human confirmation. The implementation lacks any first-use authorization protocol to vet these newly connected external tools. The software's internal logic is also designed to detect when it is operating inside a containerized environment, such as Docker or Modal. The moment the Hermes agent detects a container namespace, it silently and automatically disables its own internal safety approval checks. Operators deploy containers under the assumption that the software's native internal security layers will remain active. They do not. By equating containerization with safety, the framework abdicates security to the host machine. Unvetted MCP integrations instantly become direct network hazards. Volatile dependency trees, state-destroying configuration bugs, and bypassed execution sandboxes form an interconnected threat landscape. These traits stem from explicit architectural priorities that favor artificial intelligence research velocity. They cannot be reliably mitigated piecemeal through standard software patching. Safely harnessing the system requires constructing a strictly localized defensive perimeter strategy. First, establish an immutable version vault, pinning deployments to tested Git hashes to prevent unprompted dependency resolution. Second, mount internal state files with absolute read-only permissions to neutralize plaintext leaks. Third, force execution into heavily restricted Daytona containers, isolated aggressively from the internal network. Organizations must explicitly disable dynamic upstream plugin resolution, manually auditing and vendoring all external skills to prevent unvetted code injection. When tamed by these rigid architectural constraints, the framework provides technical teams with a powerful set of automation tools for managing complex agentic workflows. Hermes Agent is an advanced research artifact. Capturing its power requires treating it as a volatile asset and deploying it with ruthless operational insulation.